Okay, welcome to ninth International Symposium on Multidisciplinary Studies and Innovative Technologies again. This is the session 1.2, and now we can start based on the list I have. The first participant is Afet Aydın. Are you here?
Yes.
Yeah,
Oh.
you can start. You can share your screen.
Is the video necessary?
Okay. You can share if you have, or if you have presentation, you can show it.
Yes, I have the presentation. Let me share the slideshow. I think it's okay. You can see it now, right?
Yes, I can see.
Okay. Hello, everyone. I'm Ahmet Aydın. I'm Assistant Professor Doctor at Eskişehir Technical University, Computer Engineering Department. And our paper is titled as How Few-Shot Learning is Effective on Predicting Missing Values Using Reviews in a Multi-Criteria Dataset. And my co-authors are Gökhan Göksel and Zeynep Batmaz. So actually, we studied on the recommender systems and NLP, of course. The recommender systems are now the essential for the people's decisions, and they are tools to help users to manage the exponential growth of the internet and massive information. And those systems have become essential again, and in those systems we've moved from the simple 5-star ratings to more complex and multi-criteria systems, so that we are trying to enhance the recommendations by considering the multiple criteria, multiple user-evaluated dimensions. For example, when you are booking a hotel room, you might care about its location, its cleanliness, its service, and etc. And actually, this is the goal of the multi-criteria collaborative filtering, or MCF. And in those systems, actually, they enable more personalized and accurate recommendations through those dimensions. But in this one, we have a major challenge called data sparsity, because users rarely rate every criterion, and this leads to a significant missing values. And as the sparsity increases, it degrades prediction accuracy and overall system performance. Actually, this are what our problem looks like. We have a matrix of users, items, and their criteria ratings, and most of the cells are empty. For example, in our study, we used a data set about beers, and a user might rate beer's overall score, but it can skip its aroma or palette. And when the sparsity increases, the system's ability to find similar users or similar items decreases, and also the quality of the recommendation system. And there are some solutions to that. One of the common solutions to data sparsity in MCF, of course, is the missing value imputation. There are several approaches proposed by the researchers, including simple ones, the global mean-based missing value imputation. Actually, those one includes simple methods such as filling the missing values with 0, maximum, or minimum, or aggregation functions like median or mean, or the frequently occurred values. Or we have the complex ones like machine learning based and deep learning based imputations. There's a trade-off between them. Simple methods are time efficient, but they often raise some bias in the dataset, and the complex methods improves the accuracy better. Of course, a problem with the complex method is that performance of complex methods degrades sharply under high sparsity. So they deal with the sparsity until a point, but for the high sparsities, their performance degrades. And at this level, we know that large language models excel at few-shot learning from minimal data. We provide the minimal data, and we can get a response from the LLMs. In this study, we investigate the LLMs for missing value imputation in MCF systems using the textual user reviews. And our hypothesis is that LLMs ability to understand the text of the review would make them far more resilient to high sparsity than the models that only sees the rating values. And so we designed an experiment to test the LLMs directly against conventional methods. We compared LLMs, which namely Llama 3.2, Qwen 3, and Phi4 Mini, against the conventional baselines. We tested performance under varying levels of sparsity. So we created 3 data sets with 25% missing values are missing in that data set, 50% and 75% respectively. And actually, this is what our fully rated data sets and with the user reviews look like. Actually, this diagram shows our entire methodology. We have a fully rated data set. And for example, for a beer, we have the appearance, we have the rating values for the appearance, aroma, palate, taste, and overall, and we have a review from the user. And then we cluster those reviews, and we use k-means clustering algorithm to find 10 central or some exemplar reviews, and we're going to feed them to our LLMs as few shots. And then we create a sparse data set by removing ratings artificially and randomly, because this data set is fully rated and there's no missing values in that data set. So we can artificially remove some of the values to create more controlled missing valued data sets. And then for a target review with missing data, we create a prompt, of course, with the examples or few shots, and it shows the LLM the n exemplars, 10 exemplars that we have created, and then it shows the new review text. LLM's job is to read the text and fill the missing ratings, and then we parse the response and fill our dataset. So, as I mentioned, we used the beer advocate datasets in the study, which is perfect for this task. It has both rich textual reviews and 5 criterion ratings. As I mentioned, those are the appearance, aroma, palate, taste, and overall in the scale of 1 to 5. And in initial, it has around 1.5 million reviews from the 33,000 users for the 66,000 peers. And we applied some filtering on this data set. So for actually increasing the performance of the recommender systems, actually the reviews for beers with fewer than 50 ratings and those from users with fewer than 50 reviews are excluded. And after filtering, we have the 1 million reviews. And then since the LLM requires much more computing power to make them feasible, we created a representative sample of 1,000 reviews. And we did this by clustering the data into 10 groups in k-means clustering, and then randomly sampling 100 reviews without replacement from each cluster to ensure that we have captured a diverse set of opinions. And for the sparsity, as mentioned, since the B-Radicate dataset contains no missing value, so we create test cases for the missing value imputation tests and subsequently applied the imputation methods into to those missing values. So we built 3 test cases with different proportion of missingness, the 25%, 50%, and 75%. For the LLM models, we used the Llama 3.2, which contains 3 billion parameters and 28 hidden layers. QN3 has the 4 billion parameters and 36 hidden layers. Fini4 Mini has 3.84 billion parameters and 32 hidden layers. Okay, and for the baseline, actually, for the conventional methods, we have 3 categories. The statistical methods, machine learning based methods, and deep learning based methods. And we have the representative methods for each of the category. For the statistical methods, we have the mice. For the machine learning, we have the Miss Forest, and for deep learning based, we have the gain. For the evaluation metrics, we have the commonly used 2 error metrics, root mean square error, RMSE, and mean absolute error, MAE. We conduct our experiments on a computer with the given specification. And actually, this is the exact prompt we fed to the models. The system message defines the task and the 5 criteria. And the E right here is the E variable is very dynamically insert our 10 examples, our few shots actually, and their ratings. And then we provide the target review and we instruct LLM to reply in a specific format so that we can parse it with our script and get the numerical ratings from the response. Therefore, we transform the unstructured text output back into structured data. And in our experiments, we have tested 3 relatively small but powerful LLMs. We pitted them against 3 widely used conventional baselines, GAIN, mice, and Miss Forest. And the crucial difference here is that the baselines only see the rating values and do not benefit from any text. And while LLMs actually use the text and the rating values. And we evaluated all those methods using the RMSAE and MAE, where the lower scores are better. And this table shows our main results. On top, we have the conventional methods, and on bottom, we have the LLMs. Columns show the 25%, 50%, and 75% missingness levels for both RMSAE and MAE. Both scores represents the score of the method that produced the lowest error for the corresponding metric and the dataset. And for the results for datasets with a missing value percentage of 25% and 50%, Miss Forest produced the lowest scores of RMSAE, and for the MAE, Llama produced the lowest scores for the 25% and 54% missingness. For the dataset with a missing value percentage of 75, Llama produced the lowest RMSAE and MAE scores. So at the 25% and 50% missingness, results are competitive. Miss Forest, which is a random forest-based algorithm, actually, it actually gets the best RMSAE scores. Llama gets the best MAE score for those missingness levels. And at this level, it's not a clear win for either side, but for the higher sparsity levels, it changes. At 75 sparsity, the error rates for the conventional methods jump dramatically, as you can see. And Miss Forest RMSAE goes from, for example, 0.63 to 0.93. But in contrast, Llama not only wins, but its error score remains incredibly stable, achieving the best RMSE and MAE, and this is the evidence that our hypothesis is correct. Actually, this what expected. Actually, the missingness level does not affect anything on the few shot on LLMs. And this graph illustrates the point perfectly. The blue line is the average error of conventional methods, and you can see it shoots up as the dataset gets sparser. The red line is the LLM average, and for both evaluation metric, the LLM-based approach is a far more stable and robust solution. Its performance doesn't depend on having a dense dataset because it's learning from the review text, not just the sparse rating. And in conclusion, in this study, we showed that LLMs are highly effective and robust solution for the data sparsity problem in MCF systems, and actually Llama was the clear winner in the most challenging high sparsity scenario. And for the future work, we are interested in making this even better by incorporating multimodal data and building hybrid models that gets the best of both worlds. Thank you for listening, and if you have any questions, I will be glad to answer those.
Thank you for your presentation. Any questions for this study? It seems no question. Okay, thank you again.
Thank you, everyone.
We can move on to the next study. Alexandra Lurinc, are you here? Alexandra? No. We can move on to the next one. Belal Sababha. You are here?
Yes, I'm here.
Yeah.
Good morning.
Okay. We can continue with you.
Yeah, thank you. Let me share my screen. You see the screen, right?
Yes.
Okay. My name is Bilal Sababha. I'm a professor of computer engineering. I have with me here Layan, the first author in this work. The work was the senior design project of 4 students, where Layan was the lead of this project, and she is the first author. I'm going to ask her to help present the work. Hope you enjoy it. She will have more technical and deeper insights. So Layan, go ahead.
Hi everyone, I hope you're doing well. So we're here to present the design and implementation of our LLM-controlled mobile robotics platform. So our motivation for this project was integrating AI, which is a very trendy topic right now, and we should really use the best of it. So we wanted to integrate this AI into robotics so that we can have a more user-friendly and adaptable system where we can use our robots. So our objective was to build a 4-wheeled mobile robotics platform. This platform, you can use it by talking to it. So it's kind of different than other platforms that we usually see. You can talk to it, and then an LLM translates these commands that you're giving it, and then the robot kind of implements these actions. So this is our design overview. I'm going to walk you through the specifics of everything in the following slides. However, if you could see, we have the web interface. This is what the user actually interacts with. Then after that, we have a little bit of security. Then we have in the background AI processing, where we take our speech and make it into text. And then the LLM processes this text into commands that can be understood by the controller and then implemented by the sensors and motors So after that, we have full robotic execution. This is our software architecture. For the input, you can either use your voice to input commands, or you can type in the commands. If you do choose to use your voice, we have an ASR, which takes whatever you say and kind of makes it into text, so that we can send it to the LLM, and then the LLM can further understand what your command is. We do have a communication protocol between the components, and it is through Wi-Fi. They communicate through HTTPS. It is secure and fast. For our front end, we used a little bit of extra features, including login and registration, to have different profiles and different users with different, let's say, privileges. Then we have the back end, which has the API handling for the LLM, which has the database, and it has the security for everything, the API, the LLM. Then for our security, we also implemented a little bit during the project. It has a little bit of authentication, hashing, and session management. So this is a small flowchart of how the software part works. So it's just a little bit that walks you through the registration. Is the user registered or not? And then it checks the input type, if it's voice or text, and processes accordingly. If it's voice, of course, we need the ASR first. If it's text, it goes directly, and then it sends the HTTP request to the motor. So the ASR, as I previously mentioned, we used web speech because it's very fast, it's very efficient, and it's very accurate. Our workflow till now is we have the voice input, and we just covered the speech recognition. Now we will go into the LLM. The LLM, we have chosen GPT-4. As everyone probably knows, GPT is very accurate. It's very scalable. You can really use a lot about how you use GPT. It really understands language naturally. It doesn't need specific instructions. It can just understand from context. So this is why we chose GPT-4 for this integration. How we integrated GPT-4 into being an LLM for us, we prompt engineered it. So this is a small snippet of our prompt engineering. It's a little bit longer than that. I just wanted to give you a little bit into it. So basically, this ensures that our output is always in JSON. As you can see here, you must only output valid JSON. And then the user can speak in the way they do speak. It doesn't need any kind of format for it to speak for the LLM to understand it. For the security controls, we hashed the passwords, and then we had the API keys stored in environment variables for everything to be secure, and all communication was using HTTPS. So basically, we tried to implement security in every part, just a little bit. So this is our hardware overview. We covered the software. Our hardware actually uses a microcontroller, which is kind of our brains and the main point. It's an ESP32. The ESP was our like obvious choice because it has Wi-Fi, it's cost efficient, it's not an overkill for this project. We have motors, which have encoders. The encoders we needed to calculate the distance, the speed of the robot. The encoders are also powered by 5 volts from the step-down converter, which I will cover in a few points. We have sensors for obstacle detection, and for the obstacle detection, we also made an avoidance maneuver. We have H bridges for voltage control. We do have the step-down converter that I've mentioned. It takes 12 volts and makes them into 5. We have the 12-volt power source, and we have the chassis, which I will cover in the next few slides. This is a flow chart for the hardware. So basically, it just goes through how the commands are received, and then how the movement is then executed, and then we have the obstacle detection that is happening during whatever the movement is being like made or executed. The chassis, we used a laser cut black acrylic, which was the most affordable, the strongest, and the best use of a chassis for our project. For the sensors and the calibration of the sensors, we had 4 sensors. These kind of gave us a closer kind of look into how many obstacles we have, where the robot should be moving, and then it also gave us like a bigger picture for future work. So we kind of really needed these integration for the sensors to see how we can future implement sensors. Okay, so I'm going to walk you through our results. This is our main web interface. This is the first thing that you would see. If you do have a login, you can just go ahead and log in. If you don't have an account, you can register. When you register an account, we have the password requirements for further security. And then we can also see from the admin panel whatever users are being created, and then we can delete or edit the users also for more security. For the login, we have a lockout, additional security, and after you're done with all of this, you can just see your user on the top right, and you will see this interface. So the status is usually listening for a trigger word, as we mentioned that you can use the robot by voice commands. So it's usually listening for a trigger word. If you choose to speak it or not speak it, you can just say go left, and then the robot will translate it into this JSON format, as you can see. So we actually made a small, like, kind of study on where the percentage and the background noise are correlated, and for obvious reasons, as the background noise increases, the accuracy decreases significantly. So these are our results. To show you our results better, we attached a marker to the robot. This is our robot. We attached a marker to it to map how the robot moves. So here is when we told the robot to make a star. As you can see, it followed the exact path. This is the path that it drew, and it stopped right where it started. And this is when we told it to draw a square. You will see that it's not a full square, but this is because of the placement of the marker. It was placed on the back. So these were the rotations. They are 90-degree angles, as you can see. So this was a state of the robot, and then this is how it drew. It turned when it did, and it went forward when it did, and it did it in like very few seconds. So it was like almost 2 seconds per command. Here we have a small video that demonstrates how it exactly works. I'm going to show it to you. So as you can see, we've told it to make a star, and now it's moving in a star-like direction. So this was the final result for our robot, which was like an obvious success. So for future work, we really wanted to introduce robot localization. We really think it would take this project to another level. We could also create a mobile app, or we can enhance the existing web platform. We can add more features, more security. We can add voice authentication. This project is really limitless in terms of future work. We can also make it integrated with a robotic arm, or have any extra hardware components to make it useful for the elderly, for the handicapped, for anything. It's really, as I've mentioned, limitless. I think this is it. Thank you so much for having me present. If you do have any questions, I am ready to answer. And of course, my colleague is also ready to answer.
Thank you, everybody.
Thank you so much. That was pretty interesting.
Thank you.
Is there any questions for this study? We are waiting. Probably she explained everything perfectly. There's no question. Thank you again.
Thank you. Thank you.
Thank you.
So the next one is Alexander Kushnerov. Are you here, Alexander?
Yeah, I'm here. Hello, everyone.
Okay, you can start.
Okay. You can see my screen?
Yes.
Nice. Okay. Good morning, everyone. My name is Kushnir Alexander, and I am presenting our research title, Neural Network Based Method for Cybercrime Detection and Classification. We are in an area of rapid technology development. While intelligent systems offer clear advantage, they also significantly increase security risk. The sheer scale and complexity of modern cyber threats, which target data confidentiality, integrity, and availability, means the traditional security mechanisms are often influenced. Our research addresses the need more for more refined and adaptive defense system. Our research objectives are very clear. First, we want to analyze how neural network can be applied to enhance cybersecurity. Second, we aim to evaluate the effectiveness of specified deep learning model like CNNs and RNNs for threat detection. Third, we examine to the crucial role of explainable AI, also known as XAI, AI. For saying trust. Finally, our goal was to propose a more adaptive approach to security. So, why we focus on a neural network? Because they accelerate traditional system failure. They are potent tools for animal detection, progression, was data sets to find complex patterns. The adaptive capability of detection unknown zero-day attacks by analyzing behavior, and critically, as they are self-learning, meaning they can evolve their defense as threat evolve. The diagram show this diagram show a typical workflow for implementing the system. It begins with collection raw data such as network traffic or system logs. This data is the preprocessed to be clear and uniform. The core stage is trained the neural network to distinguish between normal and malicious patterns. Finally, the trained model is deployed to classify new live data and detection threats in real time. Now let's look at the specified tool. We analyze several architecture, multi-layer perceptrons, or MLMs, MLPS, are foundational. They are excellent for classification tasks such as intrusion detection or malware detection based on structured data. Next one, it's CNNs are specialized. They famous for image recognition. This capability a high effectiveness in cybersecurity for detection phishing attacks by analyzing visual elements such as counterfeit logos or by visualize network traffic data. Recurrent neural networks, especially LSTM, are designed to understand sequences. This makes them perfect for analyzing network traffic or use the logs over time, allowing them to detect behavioral anomalies or multi-step attacks. Autoencoder work differently. They are trained only on normal data. They learn to compress and reconstruct it. And when a new piece of data such as from an attack is introduce the autoencoder files to reconstruct it accordingly, plugging it's an current anomaly. Let's see practical application. In phishing detection, CNN are highly effective. They can analyze both the text of an email or fictional links and as method the visual elements, and the model can detect it config logs with the symbol change in color or shapes that are designed to device users. Similarly, deep neural network are used to provide high accuracy classification of malware. For intrusion detection, MLP can analyze user behavior factors. For instance, if a user accesses a system, for example, at 3 a.m. from a new location, the MLP can flag this as switches. Renans are even more potent for this as they analyze the sequences of behavior. They can detect a sudden spike in logins, a brute force attack, or a slow multi-stage patterns characteristic of an advanced persistent tree or ATP. The data supports this approach is shown in table for our research, which compare methods of dark line quantification, the neural network-based model, the multilayer perceptron, and the NNS cube VM architect achieved significantly higher accuracy and better prediction rate compared to traditional methods such as SVM. And this is because LNS are better at detection complex knowledge relationships in data. Neural networks are part of a broader family of classification method, which include tools like decision trees and random forest. However, as shown in this in the table, neural network architecture have specified advantage for handling to complex pattern found in cybersecurity. And furthermore, we found the hybrid methods, for example, combined with the clustering with neural networks and practically effective. This hybrid approach reduces false positive and improve overall detection accuracy. Deep learning, which user these multi-layer networks, neural networks, is really a cornerstone of modern cybersecurity. Its key advantage is the ability to process massive volume the data to find truth. A well-known example is Google Safe Browsing, which utilizes deep learning to analyze website and protection user from phishing attacks. This enable to require analysis of network traffic to identify and stop threats as they emerge. Then artificial intelligence provide the framework for automation. AI automates the entire process from detection and user behavior analysis to advanced threat response and vulnerability management. This automation is critical. It reduced to heavy workload on human security analysis, and most importantly, minimalized the time between detection and treat and neutralized it. Look like at one of these use case, user behavior analysis. The AI learns the required patterns of life for each user when it detects unusual action, such as the employers suddenly access file they never use, is flag them. We stated a real case where the start technology detection anomalous activity in financial firm allows them to prevent the data behavior break before it's happened. Even more powerful, AI enables us to transition from merely reaching to treats to proactively predictions, and by analyzing historical attack data, machine learning algorithms can identify emerging trends and forecast new attacks vector. This allows organization to stay one step ahead, whereas that one step behind, and this is already widely used in financial to prediction and prevent fraudulent transaction. However, the power comes with a critical challenge of an approach to us to as the black box problem. A neural network can tell you this is a trait, but it cannot easily tell you who. This is where explainable AI or XAI become essential. XAI provides methods like time and shape that helps explain the why behind an AI's decisions. This is not just academic. It's vital for build user trust and for meeting relation completing critical sectors. In conclusion, our research confirm that neural networks are powerful and necessary tools in modern cybersecurity. They allow us to detection complete threats that traditional methods miss. AI and deep learning transform security from relative to a proactive discipline, and we also found the hybrid methods are up and common, but most importantly, the future of the robust system depends on our ability to make them transport. The integration of XAI is critically to develop and trustful adaptive cybersecurity system that we need. Thank you for your attention.
Thank you. Is there any questions for the study? Probably no question. We can move on to the next one. Thank you again.
Thank you.
The next one is Mirka Sarela. Are you here? Probably not. The next one is Antonio Cortes. Is he here? He's not here again. The next one is Jose Cornejo, probably.
Yes, I'm here. Good morning.
Okay, you can start. Thank you.
Can you see my screen?
Yep, no problem.
Okay, perfect. Good morning, everybody. Thank you for the opportunity. My paper that is titled Industrial Collaborative and Mobile Robotics in Aerospace Manufacturing Techniques, focused in on Industry 5.0. Aerospace manufacturing is one of the most sophisticated and highly regulated industrial sectors, characterized by low production volumes, a high product complexity, and an acute demand for zero detect defect quality. Unlike the automotive sector, where high throughput and repetitive tasks dominate, aerospace production involves bespoke components and extensive manual labor. Traditional automation strategies fail to adapt effectively due to factors such as large-scale structural components, some exceeding 30 meters in length, and the requirement for frequent process customization. In response to these challenges, the industry is increasingly adopting robotics technologies that enhance flexibility, improve productivity, and maintain safety and precision under stringent regulatory conditions. To meet these demands, aerospace manufacturers are shifting towards adaptable automation frameworks supported by industrial, collaborative, and mobile robotics. These robotic systems are not only programmable but are also reconfigurable to handle multiple processes across different work cells without expensive downtime or tooling changes. For example, collaborative robots can safely operate alongside human workers, with over 68% of surveyed professionals in aerospace and defense recognizing their relevance to Industry 5.0 implementation. These platforms significantly reduce ergonomic strain and improve task repeatability, especially in manual intensive operations such as riveting, sealing, and composite layup. The integration of cobots has resulted in documented productivity improvements ranging from 12% to 27% in mixed model aircraft assembly lines. The rise of Industry 5.0 is especially significant in aerospace and defense manufacturing, where resilience, sustainability, and human centricity have emerged as strategic imperatives. As detailed in the reference 2025 year, over 72% of professionals in aerospace and defense organizations agree that resilience, defined as the ability to adapt and continue operating during external disturbances, is, is a necessary capability for future-proofing manufacturing. Additionally, the integration of cybersecure cloud platforms and blockchain has become essential in safeguarding mission-critical production data, with blockchain solutions being identified by 65% of experts as a preferred option for ensuring data integrity and traceability across distributed manufacturing networks. Digital twins technologies further exemplify the convergence of cyber-physical and human-centered systems through their ability to simulate physical environments and real-time behavior. Digital twins enable preemptive fault detection and virtual commissioning, minimizing operational risk. A particular promising development is the concept of the human digital twin, where workers' ergonomics, cognitive load, and training performance are robotics. In pilot implementations, human digital twin have reduced training time by 22% and contributed to a 15% reduction in human error during complex assembly operations. Moreover, augmented and virtual reality tools are represented over 24% of the enabling technologies used in smart aerospace manufacturing, provided immersive operator training and overlaying contextual data during maintenance tasks. These systems, when synchronized, with Internet of Things or IoT networks and big data analytics empower human operators with actionable insights in real time. Industrial robotics. Um, Industrial robotics has been pivotal in transforming manufacturing precision and repeatability, particularly in the aerospace sector, where manual operations such as drilling and fastening are prone to misalignment, fatigue errors, and ergonomic strain. Unlike the high-speed, high-volume applications in the automotive industry, aerospace components demand high customizations, large-scale part handling, and tight tolerances, often below zero point 0.2 millimeters. In response to these, automation solutions have evolved beyond traditional industrial arms into precision-driven robotic systems. A notable example is the integration of high-resolution sensors and adaptive motion planning to perform drilling and riveting on aerospace panels, eliminating variability introduced by human operators while maintaining exact standards. Such precision enhanced robotic systems are not limited to riveting. Their capability to detect and adapt to manufacturing tolerances, surface variation, and process drift positions them as central agents in adaptive aerospace manufacturing. Robots are no longer confined to fixed trajectories tasks, but can now dynamically interact with their environment, continuously refining actions based on live feedback. The described integration of visions, geometric learning, and adaptive registration illustrates how industrial robots are becoming essential not only for improving through output, but also for delivering consistent quality in applications with minimal margin for error. These innovations contribute directly to the development of smart, flexible manufacturing systems that can evolve alongside changing aerospace production needs. Collaborative robotics. They are increasingly being integrated into aerospace production lines due to their capacity for safe, adaptable human-robot interaction. Unlike traditional robots enclosed within safety cages, cobots operate in open environments and are governed by safety protocols such as force limitations, emergency stops, and speed regulation under ISO 10218 and ISO 15066 standards. In aerospace, where parts can span several meters and processes demand high dexterity and low volume flexibility, cobots offer substantial ergonomic and efficient benefits. Cobots have already demonstrated as a 47.6% reduction in composite fuselage assembly times, primarily by handling repetitive enforced extensive subtasks while human focus on delicate manual operations, ensuring a safer, more balanced division of labor. To further enhance their utility, cobots are now being equipped with precision systems and geometric learning algorithms that allow to understand part geometry, orientation, and context in real time. For example, the 2018 study by Kawali et al. Presented a system in which a laser stripe sensor mounted on the an end effector of KUKA robotic arm captured dense point cloud data from an aluminum aircraft panel. The sensor generated over 74 000 3D data points per scan, which were then filtered using an algorithm method to eliminate noise caused by reflective surfaces. In advanced human-robot interaction scenarios, this data-driven perception can be coupled with biosensor feedback. For example, a system can integrate EEG signals and heart rate variability to modulate cobot behavior in real time. increasing or decreasing task autonomy based on operator stress level. Combined with direct teaching capabilities, where technicians manually guide the robot to record trajectories. This creates an intuitive programming environment where robots can autonomously generalize procedures to new parts. Instead of scripting each new operation, the robot relies on real-time perception and previously learned geometry features to recognize whole patterns, estimate fastener orientations, and select trajectories within the same tolerance band. Such capabilities drastically reduce deployment time in high-mix production environments. Mobile robotics. Mobile robotics offer an unprecedented level of flexibility in aerospace manufacturing environments, where the size and immobility of parts, such as fuselage sections, nacelles, and wing assemblies, present various logistical constraints. Unlike fixed-base robots that require extensive power repositioning or convergence systems, mobile manipulators can autonomously navigate to various workstations or aircraft surfaces to perform precision tasks. These systems typically integrate simultaneously localization and mapping SLAM LiDAR and manipulator arms to form mobile robotic units capable of seal-land application, inspection, or drilling across large assemblies. This capability drastically reduces the need of overhead cranes, reed fixtures, or retooling processes serving both floor space and system integration time. Another benefit of mobile robotic systems is their complexity and compatibility with cyber physical production infrastructures. A fleet of autonomous mobile robots can share maps, update work status, and allocate tasks comparatively with factory-wide network. When integrated with a central mess, meaning manufacturing execution systems, these robots can collectively respond to bottlenecks, machine downtimes, or production schedule changes. Digital factory integration. The concept has become essential in designing and validating complex aerospace manufacturing systems, especially in scenarios involving hybrid automation, flexible scheduling, and multi-machine coordination. At its core, these paradigms integrate simulation, real-time data acquisition, and virtual prototyping to reduce costs and lead times while increasing productive reliability. Among the suite of digital tools employed in such environments, discrete event simulation is uniquely suited to modeling time-dependent interactions among machines, operators, transport systems, and inspection processes. By capturing both deterministic and stochastic behaviors, discrete event simulation allows engineers to predict bottlenecks, balance workloads, and assess performance in response to fault or process variability. In aerospace manufacturing, where parts tolerances are stringent and operational errors can be costly, the ability to preventively evaluate manufacturing sequences and resource configuration is crucial for system robustness and scalability. Automatic inspection and quality assurance. Precision inspection, when combined with machine learning algorithms and advanced point cloud registration, is redefining quality assurance protocols in aerospace manufacturing. Robotic systems equipped with 3D vision sensors and high-resolution cameras can now verify geometric tolerances and surface conditioning directly cost against CAD models. One of the defining features of these automated inspection architectures is the creation of traceable digital thread. Each scanned part is linked to a corresponding digital twin, storing all inspection metadata, including geometric profiles, tolerance, deviations, and defect annotations. Discussion and conclusion. The aerospace factory of the future is undergoing a paradigm shift toward interconnected, modular, and intelligent robotic ecosystem, capable of coexisting and collaborating with human operators. These systems will no longer function as isolated task executors. Instead, they will behave as cognitive agents, dynamically reconfiguring workflows, adapting to environmental variations, and optimizing performance in real time. Industry 5.0 enhances this paradigm. The integration of 5G and edge computer infrastructure will be a game changer, empowering robotic systems to make ultra fast decisions for minimal with minimal latency by processing data locally and synchronizing it with cloud platforms. Only when necessary, robots gain both autonomy and responsiveness. When combined with high fidelity digital twins, these platforms offer preemptive fault detection, predictive maintenance scheduling, and real time key performance indicator or KPI visualization. Thank you for your attention.
Thank you. Any questions? Probably not. Thank you again. The next one is Jose Luis Cabra Lopez. Are you here?
Yes, it's me. Thank you.
Okay. You can share your screen.
Okay, just a sec.
Okay.
Uh, are you watching my screen?
Now we can see it.
Okay, perfect. I'm going to do a screenshot just for the record in my university. Um, well, dear Rob, thank you very much for being here. My name is Jose Luis Cabra. I belong to the Digital University Francisco Jose de Caldas. This work is titled A Case Study of Mirror and Twin-Based Bypass of a Smartphone Face Unlock System. This work was developed with Sebastián Rodríguez Alquiladino and Darío Segura Torres, who is with me in the presentation today. Well, let's start. We will cover these 8 points at this presentation. So let's start. Well, the smartphone is the most famous device of this century. The last year achieved 1.2 billion of devices sold. This device covers a huge ecosystem regarding to the digital information that include email, social media, bank transfer, information from another people, and this is also the access key to different digital applications. There are three ways on how we can protect the data inside it. That's called a locking mechanisms. The most common are three: knowledge based and um, biometric based. So let's talk about the different vulnerabilities in knowledge base. There are three of them. Shoulder surfing attack, who is a person next to you trying to learn your secret code. Smudge attack, a trace of grease over the smartphone screen when you draw your passcode. And finally, a side channel attack when a deck device is used to acquire the information. In this case, we got a photo of a thermal image. Moving to identity base or biometric base, the most common are face and fingerprint. In the case of face recognition, we got master face, who is a common denominator face that uses Gen AI features. Image reproduction like photos, videos, etc., trying to bypass the face recognition. This kind of authentication is sensitive to accessories like the environment and power consumption. Moving to fingerprint, brute print is a brute force machine over the smartphone hardware. A master print is similar to master face. Computer-generated fingerprints try to unlock the device. Partial samples, it's a consequence to reduce the fingerprint sensor because if you reduce the sample, you are reducing the complexity. That's why it is a vulnerability. Household hacking materials, it's an example of there are different studies that people without knowledge in biometrics can hack a smartphone using a Play-Doh based material. And finally, this is also sensitive to finger condition like dirty, sweaty, or injured. However, the main issue in both cases is the public threat exposition of both threats. How can we summarize this? We got three different statements. The first one, both face and fingerprint are scalable, robust, and user-friendly solutions. But however, it exists vulnerability gaps which represent scenarios where those biometric threats might fail. So it means that we got an already privacy risks in the market. With these issues, both threats are long-term irrevocable, are highly robust. What is our proposal? Our proposal is try to enhance one vulnerability of one threat, and and we put both in a balance. Face threat is mostly exposed to fingerprints. So the next step is how the literature, what does it said about the facial smartphone attacks? We found in a first glance 7 of them. We got presentation attack when using fake facial samples like photos, videos, 3D models, max, etc. Next, we got adversarial batch, which is a addition of subtle differences in the samples trying to fool the recognition algorithm. Database attacks that include stealing, injecting, um, or biometric templates database inside our devices. Replay attack is when we capture an already used sample, trying to replay it in the next attempt. Next, we got impersonation attack, which tries to mimic um, the appearance or behavior of the right user. Facial morphing, try to merge two or more faces in what we talked before about a master key. Next, poisoning when the attacker corrupts the training data for awakening the machine learning model. So we want to focus here on trying to making a psychological profile. Real world imposters just are more creative. Well, yes, we are more sophisticated too, but they are more creative. So most of them they use low tech devices trying to bypass the recognition system. We are going to focus here in this presentation in impersonation and a presentation a specific, very specific scenario. Um, Trying to cover reflective surfaces, twins, and a specific contextual scenario. So let's expand these three moments. The research question is, how vulnerable are current smartphone face recognition systems to mirror-based, contextual, and tweet-based attacks? And what strategies can be proposed to enhance their resistance without requiring additional hardware? So, what is our methodology? We wanted to focus in three different attacks, mirror-based, tested whether a smartphone could be unlocked using the user reflection in a mirror. Um, Second, contextual awareness attack. Examine if a phone could unlock when the owner was not holding it, but their reflected image, face, and upper body was visible. These two cases may some be a bit of weird at the first time, but remember that the thief people are very dangerous, and most if Latin America countries. So this is trying to evaluate our scenario when someone is stealing the person's smartphone, and maybe they try to get in touch very close in a bathroom. So a very, very specific case. And tier one is involved identical twins where one is trained and when the smartphone is trained with one of them and the another one can unlock it. That's impersonation vulnerability. So all trials were video recorded counting success and failure rates using different conditions. We got here three different examples of what we expect. In the second experiment, just for an addition, an external person is holding the smartphone and the upper body is free. And what we want to catch here is that the smartphone gets more information that it is not already processed with current features. Our results. In the first attack, we got a 100% of successful unlocks. So it exists that we can unlock as someone else. We can unlock of devices without projected image in a mirror. So that it can be used that an impersonation and and impersonation and I forgot the another one. Sorry, impersonation and a presentation attack at the same time. Second one, it exists the awareness attack. What we are proving here that it is necessary to include a contextual mechanism in our face recognition unlocking. And finally, with our twins, we found a significant successful unlocks. Overall finding, vulnerabilities were consistent across brands and hardware configuration, showing that weakness come mainly from software and algorithm design. No camera specs are related. So um, we propose to get into in our final paper. We did a correlation with different camera specs. We didn't find any correlation between them. So we are moving that kind of weaknesses to software and algorithm design. As an improvement proposals, in the case of mirror attacks, we propose add a random on screen shapes that helps to evaluate the reflection and symmetry detection, as we can put here an example. In the case of contextual attacks, we propose the inclusion of pose landmarks to verify who and how is holding the current smartphone. Because if we already have a face recognition, we can also detect the different limbs of the person. In this case, we did this example with MediaPipe. And in addition to scan the person's body, we propose apply a contextual aware rules depending of the user scenario. It can be programmed and already um, and we can use sensors like the GPS, for example, to make that risk evaluation. Finally, in the case of twin attacks, necessary in on the smartphones and strict mode for this case of high risk users, and that also includes a multimodal factor, the inclusion of different threats, trying to prove um, the right user. Our contribution to these research are three. First one, we discovered that we can bypass our face recognition using mirror-based tools. We demonstrated for the first time that the smartphone can be unlocked using a reflection in a mirror. This kind of vulnerability is not covered in the state of the art. In the case regarding to twins, we provide to the literature a metric to show in a quantitative way this kind of vulnerability using um, current mobile smartphone brands. In the case of contextual authentication flow, we reveal that phones can be unlocked even when the owner is not holding the device, who is an out-of-logic scenario. And in addition, we propose a context awareness architecture to mitigate this issue. So thank you very much for your time, and we will see if you have some questions.
Thank you for sharing. Any questions? Okay, no questions. Thank you again for your presentation. Next one here is Sam Mohseni. Are you here? Sam. Sam's not here. Then we can proceed to George Penn.
Hello, it's on.
Okay,
You
you
listen
can
to me?
start.
Okay,
Yeah,
thank you very much. I'm gonna share first my screen, well, my camera, and then the presentation. It's easy, right?
Not yet.
Okay,
Yes, now I can see it.
okay. Thank you very much. And good morning, everyone. My name is George Pena, and I'm representing the University Technological of Peru. Today, I will be presenting the research titled Artificial Intelligence for Risk Prediction of Anemia Disease, a bioinformatics scoping review. In this work, we explore how machine learning and deep learning are being applied to support the early detection of anemia and other blood-related disorders. Specifically, we examine which AI techniques are currently used, how accurate they are, and how they compare with traditional diagnostic procedures. Our goal is to provide a clear understanding of where the field stands today and what potential AI has to support medical professionals in diagnosis anemia. Anemia is a major global health issue. According to the World Health Organization, or WHO, in their chronics, more than 1.62 billion people suffer from it, particularly children and women. Traditional diagnosis depends on laboratory tests, specialist personnel, and clinical infrastructure resources that are not always available, especially in low access environments. Because of these limitations, artificial intelligence has emerged as a promising alternative to assist medical decision making. AI can analyze hematological features such as hemoglobin, red globin, and red blood cell count, hematocrit, and mean corpuscular volume, providing fast and potentially very accurate predictions. In recent studies, performance has been remarkable. For example, in the study of Al-Kedbi et al. Report a 90.27% of accuracy, while in the study of Gomez et al. Reached a 99.82% of accuracy. For anemia classification, these results motivated us to conduct a comprehensive review of the current state of AI for anemia prediction. This study was carried out using a systematic approach based on the PRISMA methodology, like in the screen could you see, and the Peacock strategy, allowing us to clearly define our research scope and criteria. We selected scientific articles published between 2019 and 2025 from Scopus, PubMed, and Science Direct. After applying all inclusions and exclusion criteria, we end up with 25 relevant studies. The review was guided by 5 research questions focused on key hematological variables, the algorithms used, comparisons with traditional diagnosis, performance metric, and the environments where these models were tested. For the first question is, what are the most common hematological characteristics among the datasets used to train and validate predictive models of anemia and AI-based studies? We examined which hematological features are most frequently used to train AI models, The most common variables were hemoglobin HB, red blood cell count RBC, and hematocrit HCT, mean corpuscular volume like MCV. These indicators appear in over 75% of the studies, mainly because they are essential for determining the presence and severity of anemia. As shown in the figure, the average patient values in the datasets tend to fall below normal range, consistent with real clinical patterns observed in the anemia diagnosis. For the next question, what machine learning and deep learning algorithms have been applied in anemia prediction, and how are they implemented? We look at the algorithms used across the studies. Machine learning is commonly applied when working with structured data like blood tests, while deep learning is preferred for medical image or more complex relationships. The algorithms most frequently used include random forest, logistic regression, decision trees, convolutional neural networks like CNNs, recurrent neural networks like RNNs. Among these, random forest and logistic regression stood out for their reliability, interpretability, and consistently high accuracy across multiple experiments. For the next question, how do machine learning or deep learning based models compare with traditional diagnostic methods in terms of effectiveness and accuracy? We compare AI-based diagnosis with traditional clinical methods. Deep learning models using medical image achieved up to 85% accuracy, while machine learning algorithms working with hematological data reach over 95% accuracy in several studies. Traditional diagnosis can also be highly accurate, sometimes reaching 98%, but it depends heavily on trained professionals, lab equipment, and processing time. AI does not replace doctors, but it reduces human error, speed up analysis, and supports areas with limited clinical resource. For the next question, we focus on performance metric. What performance metrics, accuracy, precision, recall, AUC, ROC, most frequently report in studies that implemented AI for blood disease prediction, and how are they interpreted in relation to model quality? The most commonly reported metric was accuracy, present in 96% of the studies, with an average of 85%. The AUC ROC metric was also widely assessed, averaging around 85%, indicating solid discrimination capability. Recall, which is essential to reduce false negatives, show an average of 79%. Overall, these metrics suggest that AI models are reliable and can support clinical workflows effectively. To the next question, in which environment or context research center simulation with public dataset has the prediction of anemia by AI been applied? Well, we analyzed the environments where these models were tested. About 75% of the studies rely on public datasets, most commonly Kaggle due to their accessibility. However, only 28% of the models were validated in real clinical settings, highlighting a gap between research performance and clinical adoption. Even so, some of the models implemented in hospitals achieve high accuracy, showing that AI could soon be integrated into standard diagnostic procedures. And then we're gonna go to the next question. Overall, the 25 selected studies demonstrate a rapidly growing interest in using AI for the prediction of anemia and blood-related disorders. Machine learning, specifically random forests, showing excellent performance across different datasets, often outperforming more traditional diagnosis workflow in speed and efficiency. These findings reinforce the idea that AI has a strong potential to support medical diagnosis, reduce errors, and improve patient care, especially in resource-limited environments. Sorry. In conclusion, artificial intelligence is becoming an increasingly valuable tool in medical diagnosis. The studies review consistently show high accuracy, low error rates, and strong clinical relevance. Future research should focus on hybrid models that combine deep learning with clinical and demographic variables to enhance interpretability and applicability in real-world settings. As AI technology continues developing, it could offer faster diagnosis, improved decision making, and better treatment planning for millions of patients worldwide. Thank you very much for your attention. I would be happy to answer any questions you may have.
Thank you for sharing. Any questions? No question. Thank you again for everyone. Is there anyone left who hasn't presented their studies yet? Well, everyone did it. So we can end our session here. We're going to share all the recordings on our YouTube channel. So you can find the recordings there. YouTube channel's name will be the same as our symposium's name, so you can find it there. That was a question I wanted to answer it. So thank you again for your attendees here. Have a good day.
Thank you. Have a nice day. Goodbye.
Thank you very much for all.
Thank you very much for your attention. Thanks. Have a nice day.